I wanted to show a little bit about high-speed timing using a standoff triggered system. So this is the core system to the Triggerscope and the new Triggerscope 16. Um, what I've got set up here is an oscilloscope. So this is a four-line oscilloscope, and I've got my laptop to send commands to the device, and then I have out here on the far side, this is the uh, basically the Triggerscope board. So that board has right now a multi-line digital to analog converter in it, and it also has access for TTL controls. Now, in my previous report on software timing, I described the limitations related to software control of devices via a Windows PC and the inevitable delays that you're going to have between issuing commands, waiting for devices to talk back, and so forth. And in my example, I used a LumenCore style driver. Now, what's interesting about the LumenCore driver itself is that in the documentation it clearly states that there's really not a return value. So a lot of software will say, go out and do something, and then the software will wait until it receives a reply from the device that that thing is done. So of all the devices out there on the market, the LumenCore device is relatively fast because of the fact that the software can send the command and just make the assumption that the device is responding. And generically, that's kind of the best thing to do for device control, at least in the world of microscopy, due to the speeds required. We really don't have time for bidirectional closed loop handshaking. So anyway, that's one of the fastest systems out there again, and we could see that unless you're using the patented triggering technique that Metamorph has, there's really not a way to achieve the high-speed device control that you may want in a typical dynamic experiment. So what I've got set up here is an example of how the Triggerscope can solve that problem. Now, the Triggerscope uses a preloaded library of commands, or a list of commands to do things. So in a nutshell, you can tell it, hey, when I receive a trigger or when I step through a given program, I would like to do something on the first state. So maybe turn a line on, which would turn on, say, a laser or an LED. And then I'm either going to wait for another trigger from my camera, or I'm going to wait a specified delay time and then do something else. So that's the simple form of the standalone program capability of the Triggerscope. Now, the more complicated form is you can do that with up to, right now, 8 digital to analog lines and 8 TTL lines. In the next version, the Triggerscope 16, you'll be able to do that with up to 16 16-bit digital to analog lines and 16 TTL lines. So that's more than enough control to run almost anything. What I've got on the screen here, I'm going to zoom in to show this, is a preloaded, this is the language that allows you to talk to the Triggerscope. This does include a micromanager library, but for now I'm just using it directly. So if I ask the device what the status is, it'll tell me the current status down here of each of my programs. And the run or the configuration of this listing here is DAC 1 through 5 right now, and then TTL 1 through 5. The last value is a delay time. So if the system is set up for a certain operation mode, it'll wait 10 milliseconds before going to the next mode. Now you can see down here I have, starting off, 0 values for everything, and then the second program item is a 2000 value, so that's roughly half the range of a 12-bit DAC, which should produce about 2.5 volts. Then the DAC 4 in this case is going to produce a maximum output. Here I've got TTL 1 is going to raise high, and then turn off on the next line, high again, and then turn off in the last 2 lines. So all I'm doing here is moving these values around so that it's easy to discern changes to the system and also to demonstrate multi-line control using this system. What I'll do next is I'll arm the system. Now, from here we're going to move to an oscilloscope. This is just for people that aren't familiar with oscilloscopes, this is really just a high-speed multimeter. It's probably the best way to think about it. Now, this particular one is kind of an enthusiast one, but it's more than capable for my needs. I've got this set up right now only showing a single channel. I'll zoom out a little bit and indicate that. So I've got channel 1 here turned on. Now I'll go ahead and turn on the rest of my channels, so channel 2 and 3. That should be enough to see the two DAC lines as well as the TTL line. I've got this thing set up to run, and so what I'm going to do is, in the software, I'm going to say ARM, and I'll hit go, and the system will record, the oscilloscope will record the voltage changes that are output from my board. Now the way I set that up for people that are interested in doing this, all you do is set the trigger on whatever line's going to go high first, and then when that line goes high, you can capture this data. I'm going to see if I can zoom out a bit more. So I'm going to go ahead and tell this thing, don't collect any more data because I want to play with what I've got on the screen. And this is a little complicated for people that maybe are not used to this kind of a thing, so we're going to turn off everything but channel 1 to start. Okay, so what I'm looking at here is, it's pretty straightforward. It's a kind of like a time map starting from the left-hand side moving right, and you can see that this value here is the voltage output from channel number 1. So we go along in time, and we can see, if we look at our cursor over here, this is the cursor readout, we can see that the current value is 40 millivolts. So it's effectively nothing. That's just bias. Now, once I go to my first step, I get a value of roughly 2.6 volts, and then, or 2.4 volts, and then in my second step, I'm going to get roughly 5 volts. And again, you can see that in the upper left-hand corner here. So the question that we want to answer is, how fast can this device run, or how fast can it successfully output these commands in order to drive external devices like lasers and LEDs and so forth. So one of the ways we can test that is to say, well, my code was set up to run a 10 millisecond delay and then go to the next thing. So if we look at the time delta between the commands, we should see the total latency of the system. So I'm going to set my cursor here to look at just the very edge of this line, which is right about there. And then I'll switch the cursor over to look at the other side. Let's see here. Cursor A, channel 1, cursor B. All right. And what we're going to look at is the time delta. Now, I'm going to move this over a little bit. What we can see in the time delta, see if I can zoom this in, is roughly here, 11.2 milliseconds is the delta between cursor A and cursor B. So that tells us that it takes about 1.2 milliseconds for the code and the library and all the things going on in the microcontroller to do its job and update the output line. And what's interesting is, if we then switch this system back to its original setup here, go ahead and set everything together. There's cursor B. We'll go ahead and set these guys together. We can actually walk these lines. I'll zoom back out. And we can look at the other changes to the voltage. So here we'll drive over to this side and look at the drop and the change here, right about there. And we'll see again it's roughly, should be roughly 11 milliseconds. Yep, 11.6 milliseconds in this case. And we can go look at our last line. And so what we're seeing here is just that this response time is very, very quick. It's low latency. This is showing 11.2. Now, the next thing to look at is, how fast can the system run one channel versus another? And so in order to do that, we'll turn on channel 2. And for this, we'll go ahead and zoom in. So we're going to, this is just showing channel 2 relative. Go back to our cursor, and we'll go look, say, at channel 2. And here we're going to zoom in on the time base to look at this data very, very closely. Okay. And here we can see there's a definite change. So if I take this cursor and I move it over here to the edge of the blue line, and then I take the first side and move it over to the rise time of the yellow line, what I'm going to see is a time delta, and the time delta here is roughly 520 microseconds, so about a half a millisecond. So that's the amount of time this particular software and controller configuration is going to take in order to um, run through its internal code. And this is high-speed code that's written specifically to do this job. It's a special chunk of the code in the Triggerscope and Triggerscope 16, specifically designed to respond very, very quickly. And we can see that, roughly um, half of a millisecond is the time delay between these two changes. Now, if I add the third line, we can see that the third line actually responded almost as quickly as the second line. So for very high speed control, this is one of the most effective ways to drive your devices. The downsides to this setup are that, one, you have to have physical wires and connections going to everything. Now on modern systems, especially new laser launches and so forth, that's relatively straightforward. You can just order a custom cable made, and I do supply those with my Triggerscopes, so that you can order a custom cable to talk to your given device. And in that case, it's not that crazy. But if you're running like your own LEDs, your own lasers, you might end up having several cables connected all over the place in order to drive those. The second thing, of course, is that you need to set up the experiments that you're going to run in the Triggerscope in a way that enables this high-speed control. So there's a number of ways to do that, especially in Micromanager. You can load these programs into save files and simply load the file to a given program array and hit go, and it'll run that file for you. And then, of course, the other hurdle to jump over is just any voltage range matching. Now, the Triggerscope current version supports 0 to 5 volt devices. The Triggerscope 16 will support 0 to 10 volt devices if your application needs that. So that's just a quick overview of high-speed device control timing. And it's important to understand that this kind of timing is definitely doable with a National Instruments board, or the EasyIO controller can do things like this, or again, the Triggerscope can do this. But software control just can't go this fast, with the exception of Metamorph. And the fundamental reason for that is that Metamorph is effectively doing this kind of a thing inside a Windows computer, but they do have a patent on that technique, and therefore you're only going to find that capability inside the Metamorph software. So for those customers that want to do it in software, Metamorph's your best choice. But for those customers that want to do it in any other application or software, you're probably going to want to look at device control using this type of a setup.